Welcome to our podcast over plate tectonics. If you'd like to follow along in our book, we are on chapter 12, section 1, which is the evolution of Earth's crust. Later in our study, we'll also look at earthquakes and volcanoes. To begin with the evolution of Earth's crust, we start with continental drift, which was proposed by a scientist named Alfred Wegener, pronounced Wegener. In 1915, he came up with a hypothesis that all of Earth's continents were once put together in a larger supercontinent called Pangaea. He suggested about 2 million years ago that supercontinent broke up into pieces that have been drifting over the water like rafts. Evidence that Alfred Wegener had to support his hypothesis of continental drift included matching coastlines, that the coastlines of some continents just seem to fit together, like the eastern coastline of South America just kind of seems to fit with the western coastline of Africa. He also used matching fossils, specifically and especially of large land animals. That provided good evidence because large land animals couldn't have flown or swam across a separated ocean. So he proposed again that land must have once been together where they were able to walk across and then were separated later by the water, because again they couldn't have swam or flew across water, but they might have once been together, joined by land, and then separated by water. Wegener's last piece of evidence has to do with matching rocks and mountains. So mountain ranges appear to have been separated after Pangaea broke apart. So if we look at the Appalachian Mountains in North America, that Appalachian mountain range actually matches up with the mountain range in Northwest Africa. Similarly, Greenland and Great Britain, all that mountain range was once together in Pangaea and broke apart. Similarly, in South Africa, there's the Cape Fold Belt, which matches up also in South America. So once Pangaea broke apart, those mountain ranges became separated. The reason we believe those mountain ranges were once together is they have similar rock formations, similar rocks that are unique to each range, and again, similar or unique minerals to that area that are present on both coastlines. Wegener's hypothesis was not accepted during his lifetime because Wegener was unable to give a reason as to what the force was, the mechanism that was driving continental drift. He had the evidence, but not the reason. Dr. Harry Hess was instrumental in figuring out that reason. Dr. Hess was using sonar to find submarines, but he also ended up mapping the seafloor. Sonar is using sound waves, and you send a sound pulse down, and after it bounces and hits something, it bounces back, and the rate at which it bounces back tells you about the depth. If it comes back sooner, it's less depth. If it comes back long time, it is more depth. So he ended up mapping the seafloor, and what he found was something called a mid-ocean ridge system, or MOR for mid-ocean ridge, which was continuous and wrapping around the Earth. There's a mid-ocean ridge system in the Atlantic Ocean. If you can see there, between North America and Europe and South America and Africa, there's a mid-ocean ridge in the Atlantic floor. So Hess proposed a hypothesis that the seafloor was spreading or moving away from each other, which is to diverge, and the reason for this spreading is that magma from the mantle is being forced upward, and it's causing the crust to crack and move apart. As the ocean crust is kind of cracked and pushed to the side, we get two small mountain ranges being formed on either side of the ridge, and in the center we have a drop-down valley where that magma flows up in the middle, but again we call that drop-down valley a rift valley. Because the evidence of seafloor spreading gave us the reason why and the evidence of why plates could move, the theory of plate tectonics was established around the 1960s. So the theory of plate tectonics is that the Earth is made up of about a dozen major plates and many minor plates, and that those plates are made up of a rigid layer of uppermost mantle and then a layer of crust, and that crust is either oceanic crust or continental crust. And those plates are moving. Again, the plates are made up of the uppermost mantle and oceanic or continental crust. And so if we have Pangea here, and then those plates are moving like rafts on the mantle, they can move into their current present day locations. This is a picture of the major plates and some minor plates. So if we look at North America, find the United States here, we're on the North American plate here in brown, and so that's a major plate. If you can see, the North American plate not only has the United States, it also has a little bit of Russia. And then let's look at some other plates. There's the Pacific plate that contains mostly the Pacific Ocean. We have the Eurasian plate, which is mostly Europe and Asia. We have the Antarctic plate. We also have the South American plate, the African plate, Indian plate, and Australian plate. So those are the major plates, as I said, there's several minor plates as well. These plates can have different plate boundaries because they can either be crashing into each other, converging, coming together, or they can be diverging or moving away from each other. And so that creates different plate boundaries. And right here, we're looking at North America is separated from Eurasia. Going right down the middle is that mid-Atlantic ridge. That mid-ocean ridge is moving those two plates away from each other. So again, here we're back at a divergent plate boundary. This is where a mid-ocean ridge is separating or moving two plates apart from each other. The magma is rising up along that faulted rift valley, spreading, cooling, forming new oceanic crust, and the spreading apart is again causing a divergent boundary. Diverge means to move apart. This image is an example of a divergent plate boundary. What we're looking at is the African plate, and right here in the Red Sea there's a mid-ocean ridge in the Red Sea which is separating the African plate from the Arabian plate. So between these two plates, there's a rift valley forming in that mid-ocean ridge in the Red Sea, which new magma is coming up, pushing those two land masses apart and being filled in by the Red Sea. On the African plate itself, there's a new divergent boundary forming, which is actually going to separate the African plate, or a small piece of the African plate is going to break off from so the Somalian plate is going to break off from the Nubian plate on the African plate. So we've got a new rift valley forming there between those two pieces of African plate, which again is going to separate that African plate at some point in time. The Atlantic Ocean has a mid-ocean ridge running down it from Iceland all the way down. The Atlantic Ocean is that mid-Atlantic ridge, which is pushing Africa away from South America and likewise Europe away from North America. So the ocean floor along the mid-Atlantic ridge is newest right where it's at the ridge, right where it's being formed, and oldest as it gets closer to those continents. And here's a picture of that rift valley and divergent boundary. So the two plates are moving away from each other, and here we've got that rift valley with that new magma creeping up inside the valley and pushing that floor apart and away from each other. Switching gears, we're now going to look at a different type of plate boundary. We're now going to look at convergent plate boundaries. Converge means to come together. So this is where we have two plates that are colliding or crashing into each other. So in this image, what we're looking at is a continental crust running into an oceanic crust. And in this situation, when a continental meets an oceanic crust, the less dense continental crust stays buoyant and stays upward, whereas the denser oceanic crust gets pulled underneath. So here this oceanic crust is getting denser, so it is going to get subducted or pulled underneath. And as it does, it's going to get reheated, and that magma is going to, again, warm up, melt, and make a active volcano. But let's look at that again, that word subduction. Subduction is where one plate slides underneath the other, and that's being subducted underneath each other. So the ocean plate, again, slides underneath the continental plate in a process called subduction. At a subduction zone, we have a deep sea trench. At a subduction zone, we're going to also have a deep sea trench. Here's an example of that volcano I was talking about. The volcano is formed from, again, when that oceanic crust is pulled down under the continental crust at that deep sea trench. As it moves down into the mantle, it gets reheated and actually kind of melts, and that hot magma then moves back up underneath that land surface, and again creates that volcano and those volcanic eruptions that we see. So we know active volcanic areas are, again, at convergent plate boundaries. Again, here's a picture of Mount St. Helens in the state of Washington, which again is an example of a convergent plate boundary. So this is in Northwest America. We have the Pacific Ocean is sliding underneath the North American plate, and as it does up here in Washington and Oregon, that Pacific plate moves underneath our continental crusts, and again that magma heats up and creates created all those volcanoes, and some might be inactive and some are active perhaps today. So again, this is an example in Northwest America of a convergent plate boundary between an oceanic plate and a continental plate. We could also have a convergent plate boundary between two oceanic plates. So again, two oceanic plates can collide into each other, and again, they're both very dense oceanic crusts, so the one that will slide underneath the other one is generally just the one that's older. And again, we'll get that deep sea trench, and again, as that one subducts underneath the other, that cold ocean floor heats up as it gets pulled into the mantle, and as it heats up, that magma rises back up and creates volcanic islands. So again, at two oceanic plates converging, we get islands, more specifically volcanic islands. So here are the Aleutian Islands of Alaska. So up near Alaska, Alaska's on the Ring of Fire, so there's a lot of activity up around Alaska, but at some point there are two oceanic plates running into each other, converging up by Alaska, creating these volcanic islands known as the Aleutian Islands. Japan and Japan is another example of volcanic island arcs. So again, Japan is another example of two oceanic convergent plate boundaries. Our third type of convergent plate boundary is when two continental crusts run into each other and they do not subduct. When two continental crusts run into each other, instead of either of them subducting underneath, they both get pushed up, creating mountain ranges. So they buckle upward, forming high folded mountain ranges. Volcanic activity is absent. There is no trench. So again, this is where we get tall mountain ranges such as the Himalayas. Here where we've got the Indian plate running into the Eurasian plate. Neither of those two continental plates are subducting. They're again pushing upwards creating high mountains like Mount Everest. Here is a nice visual of the folded mountain range of the Himalayas. Our next plate boundary is called a transform plate boundary. And no new lithosphere is forming, so no new crust, no ocean crust is forming, as it is at divergent boundaries. So again, what this is two plates just sliding past each other. So they're not spreading, they're not running into each other, instead they're sliding past each other. And it's, again, the result of a transform boundary is horizontal motion of the lithosphere, or those crusts. So California is a very active state, as I'm sure you're aware. So what's happening in California is a transform plate boundary is running right along, it's the San Andreas Fault, you've probably heard of as well. So the San Andreas Fault is running right between California. So actually Los Angeles is moving north, and San Francisco is moving south. So at some point, those two cities could be side by side because they're moving horizontally towards each other. The last feature we're going to talk about are hot spots. So these tectonic plates can move over areas in the mantle that are called hot spots. That hot spot is a plume of magma rising, and as the plates move, they create in the ocean new islands as the island sits on that hot spot. And as the plate moves, we create a new island. So the Hawaiian Islands are a great example. They were formed by sitting over a hot spot. Yellowstone is currently over a continental hot spot. As you can see, the hot spot is in a fixed location. And these are the Hawaiian Islands that we're looking at. So Hawaii, the youngest island, is currently over that fixed hot spot. But these older islands, Kauai is the oldest, because again the Pacific plate, if you can see, is moving to the left, or the kind of the northwest of our slide. So Kauai was the oldest when it sat over the hot spot, but then the plate moved, and then it formed Oahu. The plate moved some more, formed Maui, and again now Hawaii is being formed. It's an active volcano over the current fixed hot spot. In this video, we talked about how Alfred Wegener proposed the idea of continental drift. However, he didn't have the force behind continental drift. Seafloor spreading is what is the evidence for the why, the how, that plates are moving. There are 12 major plates, and they are moving away from each other at divergent plate boundaries. They are coming together at convergent plate boundaries, and we talked about what happens at a continental oceanic convergent plate boundary. The oceanic floor subducts underneath the continent. At an oceanic plate boundary, one of the ocean floors will subduct and create volcanic islands. And at a continental convergent boundary, mountains will be formed, because neither continent will subduct. They will both push each other up. At transform plate boundaries, we have two plates that are neither running into each other nor away from each other. They are sliding past each other horizontally. Finally, we talked about how a plate can move over a hot spot, which is a fixed hot plume of magma that can create active volcanoes. Thank you for watching.